So Unit 2 deals with two things. There's two parts, two sections of Unit 2. The first section, which we're going to do tonight and next week, is business-related statistics. The second section of Unit 2 is merchandising, markups, markdowns, and stuff like that. So let's take a look at statistics. There's a lot we could cover about statistics, and we're going to squeeze what we can into 2 weeks. But to deal with statistics, we first have to deal with some vocabulary. First of all, what is statistics? Well, as a field of study, statistics is nothing more than the gathering of data and using it to either describe or predict. Now, by describe, I mean describing the current characteristics of some group of interest, or predict a characteristic that we don't yet know about them, or predict what's going to happen under given conditions that are coming up in the future. So I talked about that group that we want to, that group of interest. That is actually what we call a population. So that population is the group that we want to learn about. And whether that's just we want to gather information to describe that group or better define that group, or if we want to gather information to predict something about that group or make a decision about that group. The population is not as easy as it appears to define. And it's very, very important to define it correctly. Because if we don't define that population well, it's virtually impossible to do the rest of what we need to do with statistics accurately. Let's look at some examples and I'll show you what I mean. Let's say, well, election year, we're all probably sick of hearing about it at this point. I know I am. But let's say we want to learn about the presidential election. And what we want to know is who will win? Who are we going to be stuck with for the next 4 years? Well, if we look at this, the population of interest can be kind of deceiving. A lot of people would say, well, our population of interest, the population is the votes. Well, we're not really looking to learn about the votes themselves. What we want to learn about are, well, some people would say the candidates. Again, it's not the candidates that are going to determine who wins. Who's going to determine who wins? The voters. So we're not concerned about the candidates. We're not concerned about the votes. We're concerned about the voters who are going to be casting that vote. Those are the people, that's what we want to learn about in this case. But we don't want to learn about all voters in the United States. We only care about those who will vote in the next election. So the voters who are going to vote. Now, we have to be careful. There's going to be a lot of people who aren't eligible voters that are going to vote in that election as well. So technically what we're really looking at is just people who will vote in that election, or who will cast a vote in that election. Other cases, it's a little bit more defined. If we're looking at quality control issues, we might look at, looking at interest in looking at defective parts. If we're studying defective parts, generally the population we're interested in is all of that type of part produced. So we're not learning about, we don't care about just the defective ones, we care about all the parts so that we can use that information to predict which ones will be defective, or how many will be defective, or patterns in the defectives. So that's our population, that whole group that we want to learn about. We don't generally study the population. We would like to know information about the population. Information about the population, or items that describe the population, are called parameters. So it's information describing the population. Now, I gotta be careful with that definition because that definition can be a little deceiving. A lot of people think, oh, well, I'm just trying to define the population. No, that's not it. When we say, what's the parameters of the population? If we're looking at the election, they'll start in, well, it's the people who will vote. No, that's defining the population. The population are the people who will vote. The parameter is a piece of information that describes a characteristic of that population. So maybe the parameter is, can I spell characteristic? It should be E. Is that better? That's probably just because my writing's so sloppy. I'll try it again. Does that look better? Still looks off, but close enough. Let's say 40%. I'm sorry, there's a reason I'm a math teacher. 40% will vote for candidate A. That's describing, we're trying to describe the population with this, a characteristic of the population. That's a parameter. Technically, I should probably have said 40% of all voters, or of all who will vote, will vote for candidate A. So we're clarifying that we are talking about all of those in our population of interest. In most cases, we cannot study the population because of a lot of reasons. It's large, hard to get to all of them, financial limitations or whatever. So most of the time, what we study is called a sample. A sample is a smaller group from the population, out of the population. Reasons why we choose a sample are numerous. One, size. Size can affect us in a couple of different ways. Time being the obvious one. There's no way I could ever possibly contact every person who's going to vote in that next election. It would take me probably years to contact all those people because there are literally hundreds of millions of them. I believe there's what, like 180 million registered voters in the United States. Contacting will be almost impossible. I wouldn't have the time. Second factor that comes in with the size is money. It'd be very expensive to hire people. I mean, I can't do it myself, so maybe I hire hundreds of people to call them to try to get it done. That'd be very expensive. I don't have that type of money. The third one, different words can be put in here, but I'm just going to say logistical. And that's really two kind of things. One is I can't define them. There's absolutely no way of knowing right now who's in that population even. Because there are people that right now will say, I don't really care who wins. I'm not going to vote. That in the next couple of weeks, something might happen that get them wound up and they decide they're going to vote in the next election. Or the other way around, there might be people that are really fired up and absolutely certain they're going to vote. And something comes up on election day, they get busy and they just don't make it there to vote. So I mean, we can't accurately define everybody who's in that population, so we can't possibly gather information from all of them. Second is, this is another one that's more difficult to word, changes over time. Because the population is so large, I have to be able to gather the information from people, to be accurate, to be valid data, I have to gather that information in a small enough period of time that it's all done under the same conditions. Well, what do I mean? Well, let's say I start today calling potential voters and asking who they plan to vote for. That's fine. But let's say Saturday, one of the candidates says something really stupid and offensive and angers a lot of the voters. Well, some of those voters I already called may have changed their mind. Now, after hearing that, they're going to vote for the other person now, or vote for somebody else. The conditions under which I'm gathering that information have changed. So I'm not gathering, if I keep calling voters and keep asking who they're planning to vote for, I'm gathering data under different conditions. It's no longer the same population I'm looking at because there have been things that have changed them. So I've got to be very careful. I mean, I know that's time again, but it's a different reason why time. It's not that I don't have the time. It's that changes over time have affected the information I'm gathering now. So size of a population is obviously the biggest reason why we would take a sample, and all these different sub-reasons fall under it. If we have a really small population, yeah, by all means, gather the data from the whole population. Well, in that case, a lot of the stuff we talked about in statistics isn't really necessary. And that's a big portion of our statistics, is gathering information from a sample so we can use it to describe a population. Another reason I'm going to put up there, obviously what I've named is probably 1 through 5 for reasons that we use a sample instead of gathering from the whole population. This next one's on a little different vein. In manufacturing, we a lot of times do quality testing on products. So I'm just going to say destructive testing. For example, let's say we're dealing with child car seats. We need to know that the belts in those seats are strong enough to withstand the force that they're going to need to in an accident. So what are we going to do? We're going to take one of those belts, we're going to put it in a machine that's going to stretch it until it breaks to see how much force it takes to break that seat belt. Well, can we test every seat belt? Why not? Well, we broke them. So if we test every one, they're all broken, we have nothing left to sell. So we have to take a sample, a smaller portion, and test them and trust that if the quality of our sample is good enough, that the quality of all of them produced is going to be good enough as well. So we can't destroy everything by testing it. That's scary? Oh, bad example, I'm sorry. So anyway, the example that I used to use, because I actually was part of the study, was for soda cans, aluminum soda cans. I actually helped set up manufacturing to punch out. The soda cans used to have a separate bottom that was folded, just like the top is folded into it. The bottom used to be folded into it. Well, now it's just a round disc of aluminum they punch out to make the whole body and the bottom of the can molded together. And so they did that, but the cans have to be able to withstand a certain amount of force because they have to be able to stack them to the height of a truck. So they had to test the amount of force that they could handle. That was the same thing. If you test every can that's being produced, you're crushing them all, and there's nothing left to use. So they had to figure out how many cans or what portion of the cans they had to pull off the line and test to make sure that they were all good, or that reasonably sure that they're all good. You can never be totally sure. There are other reasons out there to select a sample rather than a population, but I think you guys get the picture that we just can't physically get to everybody in the population, so we select that sample. Just like a parameter is a piece of information describing the whole population, a statistic is a piece of information describing, again, a characteristic or a trait. I'm going to use trait so I don't have to spell characteristic of the sample. So we've chosen this sample. Actually, choosing the sample itself is one of the more vital operations in statistics. A poorly chosen sample is about the most worthless thing you'll ever do. If the sample isn't chosen correctly, everything you do after that is invalid. So to choose a sample, there are two things we worry about. One is proper size to get a good sample. I should put in parentheses up here, a good sample. We're not going to discuss too much about size in here. There are all sorts of different theories out there on size, different formulas. Some of them say it's the estimated size of the population divided by whatever, square rooted, or all sorts of different formulas for comparing required sample size to the size of the population. Some textbooks say at least 30 is the minimum sample size. One of the reasons they say that is a lot of the methods that they use in advanced statistics don't work if you don't have at least 30 data points. So it's kind of arbitrary that they use that. For our purposes, we're just going to say, hey, take a sample that's large enough. And common sense is going to rule that. If I want to know what's the average age of students at WITC, and I go out in the hallway and I just take the next two students I see and ask them how old they are, that's obviously not a big enough sample. Now that sample's bad in a lot of other ways too, which we'll get into, but the sample needs to be large enough. And obviously, the reason the sample has to be chosen well is because of something called sampling error. Now, I know I'm going outside my list here for a second. Sampling error is a difference in the characteristics of the sample compared to the population. So let's go back to that election example again. So let's say I choose a sample and I call up the people, and 70% of the people I survey say they're going to vote for candidate A. But yet, realistically, only 40% of the whole population really plans on voting for candidate A. That's a sampling error. That's a difference between what the information I gathered from my sample and what the real information is about the whole population. So it could be that I had a bad sample, or it could be just random differences. So there are two causes of sampling error. The first one, or A I'm going to call it, is a bad sample. The second one is just random chance. It's possible that I just randomly happen to select people without trying and without doing anything wrong. I just randomly happen to select a large number of people that planned on voting for candidate A. Nothing I can do to stop that. But this ties back into our size. The larger the sample, less chance there is of having a sample that's off just by random chance. So we have to have proper size. Next is the selection process, and this is where it gets more complicated. The example where I said I'm just going to walk out in the hallway and find the next two students and ask them their age, well, that selection process is bad in so many ways. Not only is the sample too small, but it's not random. Because I just went out in the hallway and just had the first two students I saw. I took convenient data. The selection process must, in order to be good, must be random. To be random, that means every member of the population. Must have an equal chance of being in the sample. So if I just go out in the hallway and grab the first two students, first of all, students from Ashland, Superior, New Richmond, Hayward, Ladysmith, they have no chance of being in that sample because they're not here. Second, students that are here only in the morning have no chance of being chosen. Students who are only online have no chance. Only students that would be in this campus, in this hallway at this time of day have any chance of being chosen. So it's definitely not random. So let's look at some sampling methods. One sampling method I'm going to look at put names in a hat. I'm going to take the name of every student. Now, I might be their name, it might be their student ID number, whatever. I'm going to put them in the hat. I'm going to draw out however many I'm going to use. Now I'm going to define something here. I'm going to use the letter N. I'm going to draw out N. N represents the number of items in the sample. So let's say I'm going to I decide that 200 students is a big enough sample. So I'm going to draw out 200. N would equal 200. Now this is obviously a simplification. I'm not necessarily putting them all into a hat and drawing them out. I might use a computer program to select them. I might use some other method of selecting them, but it's just kind of the old-fashioned way of describing it is you just draw them out of a hat. Every person that's a student in the population has an equal chance of being chosen. The second method I'm going to do is going to be called a cluster sample. In a cluster sample, what I'm going to do, still looking at that student example, I'm going to randomly choose classes, and I'm going to survey everybody in the class. So I'm going to randomly choose, let's say I need, say 200 students again. Your classes have an average of 15 students. So I figure I need, what does that come out to be, like 14 classes to get me to 200. So I'm going to randomly select 14 classes that meet throughout the college. Then I'm going to go to each of those classes and I'm going to survey every student in each of those classes. Every class had an equal chance of getting chosen, so every student had an equal chance of getting chosen. Why would you want to do a sample like this? Well, convenience. Well, not convenient. I've got to be careful about convenience. It saves me time and money. Because if I have to get a survey of those students, if I have to go to that classroom to give a student a survey, I just will survey the whole class. Think of like door-to-door surveys. If you have to survey people door-to-door, once you've stopped there, you just will go to the neighbors because they're right there. If I'm going to survey, let's say I'm doing a survey on cable television or cable internet in a city, and who's interested in it and who's not. I could randomly select people scattered throughout the city, but then I've got to drive all over the city and interview each of them separately if I'm going to go door to door. It'd make more sense, it'd be more time and money efficient to select a whole block and go to that block, park my car, and walk around the block and survey everybody on that block. Then randomly select other blocks. That way I'm concentrating my effort and not wasting time. So a cluster sample is random because everybody has an equal chance of being selected. Third type is what we're going to call the stratified sample. Now, a stratified sample I'm going to start by dividing the whole population into groups. What do I mean by groups? Like there's groups that belong together. For example, I might do only online students as one group, students at Rice Lake is one group, students at New Richmond's another group, students at Ashland, Superior, Hayward, Ladysmith. I might even separate each campus into daytime students and nighttime students so that I know I have students representing from each group. Because maybe students that are in night classes, maybe they're more likely to have been out of school for a while and have jobs, so their age might be different from students that are in daytime classes. I might have divided into groups of full-time students and part-time students. And then once I've divided it into those groups, I randomly select some from each group. Another example of this might be if you're running a company and you want to survey your employees to see whether they prefer having their lunch hour from 11 to noon or from noon to 1. And let's say your employees are, 80% of your employees are full-time and 20% are part-time. Well, if I just threw all the names of my employees in a hat and drew out names, there's a good chance that most, if not all, of the people I select for my sample are going to be full-time employees, because that's overwhelmingly full-time employees in my whole population. So what I might do is I might divide it up into full-time employees and part-time employees, and then select a certain number from the full-time and then a certain number from the part-time. Now, let's say, to keep it simple, I'm only going to select 10 employees to be in my sample. Well, if 80% of my employees are full-time, I'll select 8 for my sample from the full-time. If 20% is part-time, I'll select 2 from the part-timers to be in my sample. Now the sample represents my population. 80% of the sample is full-time, 20% is part-time. So I know that the part-timers have been represented equally in that sample. So the same with like night students and day students or whatever if I'm sampling students. This again is random because if I do this correctly proportionally from each group, each student still has the same probability of being chosen, equal probability of being chosen. I might have a systematic sample. Systematic sample, I randomly choose a starting point. And then the system does the rest. For the students, maybe I've got my students lined up numbered from 1 through 800, or however many students are on the list. And I know that, okay, out of that 800 students, I want to sample 80 of them. So that's 1/10 of the students. So I'll randomly choose a number between 1 and 10. Maybe I choose 4. So that means the system then is going to tell me who to choose after. I'll sample the 4th student, the 14th student, the 24th student, 34th student, and so on. I might, if the manufacturing setting where let's go back to the soda cans. I'm going to test the soda cans for their strength. Same thing. I might randomly select a number between, let's say I decide I have to test 1 out of every 100 cans. I'll randomly select a number between 1 and 100. I might choose 52 or whatever comes up. I could put those 1 through 100 in a hat and draw it out. It doesn't matter. Once I've selected that first number, if it's 52, I'll test the 50-second can off the line. Then I'll test the 150-second can and the 250-second can as the time goes on. The system decides everything after the starting point is selected. So I don't have to keep randomly choosing. Systematic sampling saves time because you only have to choose the starting point. You don't have to go through that random process over and over again. Now, every so often, like every day, if I'm looking at testing the soda cans, every day I come in, I should select a new random number, and that's the one I'm going to test out of every 100 that day. So it shouldn't stay the same over extended periods of time. The next one we're going to look at is called the convenience sample. Let's say that I decide that I need to select 80 students for my sample. So I've got 20 students in each class. I'm just going to sample the next 4 classes I have and survey them. Well, I'm doing that because it's easy and it's readily available to me. But again, that's not a good sample. I'm only sampling students that take a math class. We might have a lot of students, well, we do have a lot of students, they're not currently taking a math class. So it's not a good sample. Another example is I might go out in the hallway and just survey the first 80 students I see. Again, I'm only selecting students that would be in the hallway at this location at that moment in time. So it's very convenient. This method is not random. So that method, the convenience sample, is not acceptable in most cases. There are a few cases where it is acceptable. If the data is not that important that we're accurate, or if time is super critical where I have to gather the data really quickly and get an estimate. And again, the precision of that data is not really important. I just need to get an estimate really quickly. So I can take it, I just have to know that I can't rely on that data to do any really serious predicting or anything like that. So these first 4 are all random. One of them is what we call simple random. Simple random is not only random in that each item in the population has an equal chance of being in the sample, but it's also random in the way that each possible sample of size n, remember we said n is the size of our sample, has the same chance. What do we mean by that? Well, I go back to that stratified sample. I had the part-time employees and the full-time employees. It's very possible if I'm choosing 10 employees to survey that all 10 of them could have been out of the full-time employees. Well, I purposely stratified it so that I made sure I did select some from the part-timers. Well, that is not simply random because now it's not possible to choose a group that's all full-timers. You know, simply random, that possibility would be there. Or it's very unlikely, but it would also be possible that I happen to randomly choose a sample that is all part-timers. Again, very unlikely, but that would be simply random, would allow that possibility. Only one of the methods we described is simply random, and that is this first one. In fact, that is often called the simple random sampling technique. That is obviously the best. The simple random sample is the most statistically accurate method of sampling, but you can see there are reasons why the other ones would be used in those cases, even though they're not quite as mathematically reliable. So anyway, now that we've gathered data, we have to look at what it is we're gathering. Statistics is about asking a question. And the data we gather is the answer to that question. The question might be, what's your favorite color? The question might be, what is your age? It might be, what's your GPA? How many classes are you taking? Do you like your major? All sorts of different questions. The answer to that question is the data that we're going to gather. So the type of data we gather, there's 2 main categories. One is called categorical. Depending on the textbook, sometimes called qualitative. because it's measuring a quality of the items in the population or sample. And it puts them into a category, is why it's called categorical. And so the reason that in this type of data, the answer to that question puts you into a category. An example might be favorite color. The answer blue, red, black, green, it puts you in the category of people that like that color. All yes or no questions are categorical or qualitative because it puts you in the, either you're in the group or you're out of the group. So it puts you in a category or measures a quality about you. Then we have numerical or quantitative. Quantitative because it's measuring a quantity or a number. Numerical because, yes, the answer to that question is going to be a number. And this is divided into two main groups. Discrete and continuous. There's a lot of different definitions for these. The ones I like the best are this. Discrete are counted, and continuous are measured. A lot of the definitions for discrete involve talking about gaps between data. Basically what discrete is you're counting. If I ask you, how many kids do you have? You're going to count 0, 1, 2, 3, 4, 5. You cannot have 3.5 kids. No. If I ask you how many classes you're taking, same thing. 0, 1, 2, 3, 4, 5. You're not taking 2.5 classes. You're either taking the class or you're not. That's discrete. That's counted data. You cannot have, there's gaps between the numbers. You cannot have numbers in between. Continuous is measured data. I might ask, how tall are you? Well, now you'd have to measure. You know, I might be 67.3 inches. Well, continuous, there is no limit to the values. I could keep going. It could be 67.3 or it could be 67.3258. You know, I could keep going. I could get more and more precise as I wanted to. Another definition of continuous is no matter how close together two data values are, it's possible to find one in between them. So you might be 67.3 inches tall. Another person might be 67.4 inches tall. Even though you're that close, it's still possible to find somebody whose height is in between yours. So that's continuous. As we go to analyze data and organize data, that's going to be very important, those two different types. And that is actually going to be our next step, is we're going to look at organizing data. So when we go to organize data, we have this, we start out with this list of raw data, the responses from our survey from a sample or the results of whatever test we did. Let's say we'll stick with that favorite color. Let's say I asked what your favorite color is and I get responses. I'm going to limit your responses to blue, red, and green. So let's say I get blue, blue, red, green, red, red, green, blue, red, red. So 1, 2, 3, 4, 5, 6. Blue, green, blue, blue, red, red, green, 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 red. There's 20 responses. Looking at that set of data, can you tell me which response is given the most often? Now, this is just 20. Now, some of you are starting to count, but don't do that. Just look at it. And here's the thing. The human brain can only comprehend between 7 and 13 objects at once. So when we look at this data, we cannot see this whole set at once. But if I'm looking right here, what appears to be the most popular color? Well, blue is 5 out of those 8, isn't it? If I'm looking In here, what appears to be the most popular? Red. There's a really high concentration of red. Or over here, it's starting to look like green is pretty popular. So it's necessary to organize that data so we can get a better picture of how it falls. The tool we use, the first step, or the first tool that we use, is something called a frequency distribution. What a frequency distribution does is it lists, for categorical data or qualitative data, it lists our different possible responses, or all the responses that we got. In this case, we limited those responses to red, blue, and green. I'm just going to label that color because, oh, they're colors. Now, on the other side of the table, we list the frequency. How often did they occur in our sample? Now, I'm going to add another column into this table that normally isn't there. It's called the tally. I'm just going to use this column in order to count these up. So I'm going to look at this here. I've got blue and blue, so 1, 2 tallies. Red, green, so 1, 2. Red, red. Green, blue. Red, red. Blue, green. Blue, blue. Red, red. Green, green, green. And red. Now from those tallies, I can see that red is 8, blue is 6, and green is 6. Some of you may have looked at that original set of numbers and may have been able to pick out that red was the most popular, but how many of you would have guessed that blue and green were equally popular? Not very many, right? Most would guess from that set that blue was definitely more popular than green, but it's not. Now that it's in a frequency table, though, it is very, very easy to say, hey, red is the most popular one. Now, of course, I wouldn't leave it like that. I would list it like this. I would redo this. So I have my colors, red, blue, and green. And my frequency, 8, oops, make it legible, 8, 6, and 6. That tally is just a working column. Once I'm done, I take that out. My final finished table does not have that in it. This is a raw frequency table, or just a frequency table. There are times where we want to know something called relative frequency. The relative frequency tells us what portion of the whole is each value. To find the relative frequency, the first step we need to do is find the total frequency. If we add these all up, we get 20 total responses. The relative frequency can be either given as a decimal or a percent. If I divide each frequency by that total, 8 divided by 20 is 0.4. 6 divided by 20 is 0.3. The other 6 divided by 20 is still 0.3. Those are my relative frequencies. That better add up to 1.0, or really close to it. There might be round off errors. 20 was an easy one to divide by. If it was 30, you might get some decimals that you have to round off, and so on. So I could list it as 0.3 or 0.4, 0.3, or 0.3, or I could change them to 40%, 30%, and 30%. Either way is fine. Some textbooks will separate it as relative frequency and percent frequency, but they really are describing the same thing. It's what portion of the whole amount is being represented there. Here there's only 3 possible responses, so it's really easy to look at this and say, hey, red's the most common one. But what if there were 20 different colors that were in here? It would be a little bit more tedious to look through that table and pick out the one that was the most popular. So there are other ways of representing this data. The next step would be to represent it graphically. I could do a bar graph. All of us are pretty much familiar with bar graphs. A bar graph can be vertical or horizontal. I could have my colors on the side here and numbers down the bottom, and I could have my bars going this way. Obviously, those aren't accurate. Or I could have my colors, my categories along the bottom. My number scale at the side, my bars going vertically. I need to make sure my number scale goes up at least as high as the largest number. Then I can put my bars in here. Red was 8. Goes up to 8. Blue was 6. Green was 6. Now on this graph, even if there is 20 colors listed here, I can very quickly look at the graph and see which one's the tallest. So the graph is a lot quicker to find that largest or smallest value, or to compare to. I can see very quickly if I'm comparing the blue to green that they're the same size here. Now I only went up to 8 items here, so it's pretty simple. I can look at this and say pretty surely that's exactly 6 people chose blue, or exactly 8 people chose red. But if it's a large number, let's say that this really isn't 8, this is 80. Well, now is that really right at 80, or is it 78, 79? A graph is not good for getting exact numbers, it's good for comparing values. If I wanted the exact numbers of each category, then I would want to go back to one of these tables. The table gives me the exact values. I realize I'm going past break time, but just a couple more minutes here to finish up our qualitative data. The other type of graph that we can use for qualitative data is a pie graph, sometimes called a circle graph. A pie graph generally is used to represent the percents or the relative data. If this were 20 years ago, we would take those that percent frequency or relative frequency. Red was 40% up here. And we would find 40% of 360 degrees and take our protractor out and measure it out. Well, these days, if we want a perfect circle graph or pie chart, we're going to use Excel or some other computer program that's going to give it to us perfectly. So we're just going to be rough about it here. We don't need to be perfect and pretty. We know that red, well, let's look at this. We know that half of that circle is what percent? 50%. A quarter of the circle would be 25%. Red was 40%. So that's going to be less than half, about that. That's going to be our red. Blue was 30%. That's going to be a little bit more than a quarter. Something like that. That's blue. Green was also 30%. So that better be really, really close or exactly the same size as the blue. For our purposes, that's close enough to make a circle graph. Okay, I'm a few minutes past break, so let's go ahead and take our break here. It's 6:23, so we'll start up again at 6:33.